This example comes out of 3.3, rates of change in natural sciences. So I'll finish this section off with a biology example. Lots of times in biology we talk about populations, and the population can be related to time in some way, and depends what kind of population it is. A lot of populations grow exponentially, and so later when we learn how to take derivatives of exponential functions, it would probably be a more realistic biology example. But in this case, we're going to look at the rate of change of population growth with respect to time, or population change, because obviously not all populations are growing with respect to time. So with delta n over delta t, or in the case of, we'd have f of t2 minus f of t1, looks awfully familiar, I hope, over t2 minus t1. And in the case of, so that would be, for an average growth rate. If we're looking for instantaneous, we once again would be doing the derivative. We'd be saying what's the limit as delta t goes to 0 of delta n over delta t, which is just dn by dt. So for this example, they're approximating the growth of this population as n equals 650 plus 120t plus 16t squared. And we're talking about bacteria after t hours. As I said a minute ago, it is more realistic that these would be growing exponentially, and the truth is any growth curve in bio is approximate, because populations don't follow perfect smooth curves. But if you plot a bunch of data and do some analysis of them, you can come up with an equation, something like this. So if they ask me then to find the growth rate after 4 hours, is how they word it in the book. I probably would prefer, and we had a little discussion about this in class, the word at 4 hours. Either way, they're not giving us two separate times. They're saying at t equals 4, what's the growth rate of these bacteria? How fast are they growing? So it is instantaneous, and we're going to say, well, dn by dt when t equals 4 is equal to the derivative of that, which is 120 plus 32 times t. And so when I sub in 4, I've got 120 plus 32 times 4. And if you multiply that out, you get 248. And the units here would just be bacteria per minute, per hour was our unit of time. So at that moment, this bacteria population is growing at approximately 248 bacteria per hour. I said earlier in the lesson, you could do basically anything that's changing with this same kind of method. So I won't do a chemistry example, but you could have concentrations of reactants over time kind of thing, and do reaction rate style questions. We will do lots and lots of rate questions relating things to time, how they change over time, in 3.5. That's basically what the meat of this unit is about, is called related rates, and that's what comes next.